morning and a very warm welcome to this presentation. I am Nishtejit Singh of Chemical Engineering Department, third year student. This presentation is an assignment for the subject of CRE, which we are studying in 6th semester under the guidance of Dr. Shashikant Yadav. So, uh, it is this assignment is under the guidance and a submission to Dr. Shashikant Yadav. So the topic of the assignment and this presentation is mechanism of catalyst deactivation. Now, introduction. In this presentation, we will see how the activity of the catalyst decreases with time. So with deactivating catalyst, regeneration or replacement is necessary from time to time. So basically, as we do a reaction, after some time, our catalyst become deactivated. There are many factors that correspond to that are involved behind this process. So to get a good yield, we need a catalyst to be active. So that is why we are studying this topic. If deactivation is rapid and caused by a deposition and a physical blocking of the surface, this process is often termed fouling. Removal of this solid is termed as regeneration. So this is how we are get rid of the deactivation in catalyst. So the process is regeneration. So the carbon deposition during catalytic cracking is a common example of fouling, which actually deactivates the catalyst and affects the yield of the product in a reaction. If the catalyst surface is slowly modified by chemisorption on the active sites by material which are not easily removed, then the process is called poisoning. And another definition for the same process, restoration of activity where possible is called reactivation. So this is the process that is opposite to deactivation of the catalyst. If the adsorption is reversible, then a change in operating condition may be sufficient to reactivate the catalyst. If the absorption is not reversible, then we have permanent poisoning and we cannot do anything about that catalyst. The term deactivation is used for all type of catalyst decay and any material which deposits on the surface to lower its activity, a poison. In this presentation, we will be studying the mechanism of catalyst decay. If the adsorption is not reversible, then we have permanent poisoning, that is, the deactivation will be permanent. This may require a chemical treatment of the surface or a complete replacement of the spent catalyst, because then the yield that will be returned by that reaction will not be as good enough, as the catalyst is not working at a proper rate. Moving on, the deactivation of catalyst depends on following factors. There are three factors that mainly affects the deactivation process of catalyst. First is decay reactions, second is pore diffusion, and the third is additional factors that influence the decay. Now we're going to study these three in deep manner. So first, decay reaction. Decay occurs in four ways. The reactant may produce a side product which deposits on the deactivated surface. This is called parallel deactivation, the name for the process. Now, the reaction product may decompose or react further to produce a material which then deposits on and deactivate the surface. This is called series deactivation. An impurity in the feed may deposit on the deactivated surface. This is called side-by-side deactivation. So these are the three ways, and the key difference in these three forms of decay reactions is that the deposition depends respectively on the concentration of reactant, product, and some other substances in the feed. Since the distribution of these substances will vary with position in the pellet, The location of deactivation will depend on which decay reaction is occurring. Now moving on to the fourth way for the decay process, the structural modification or sintering of the catalyst surface caused by exposure of the catalyst to extreme conditions. This type of decay is dependent on the time that the catalyst spent in the high temperature environment, and since it is unaffected by the materials in the gas stream, we call it independent deactivation. So this was the last and the fourth part of the decay process. Now moving on to the second factor, that is pore diffusion. For a pellet, pore diffusion may strongly influence the progress of catalyst decay. First, consider parallel deactivation. We know that reactant may either be evenly distributed throughout the pellet or may be found close to the exterior surface. Thus, the poison will be deposited in a like manner uniformly for no pore resistance and at the exterior for strong pore resistance. In the extreme of very strong diffusional resistance, a thin shell at the outside of the pellet becomes poison. This shell thickens with time and the deactivation front moves inward. We call this the shell model of poison. Consider series deactivation. In the regime of strong pore regime, concentration of product R is higher within the pellet at the exterior. Since R is the source of the poison, the latter deposits in higher concentration within the pellet interior. Hence, we can have poisoning from the inside out for series deactivation. Finally, consider side-by-side deactivation. Whatever the concentration of reactants and products may be, the rate at which the poison from the feed reacts with the surface determines where it deposits. So, for a small poison, rate constant at the poison penetrates the pellet uniformly and deactivates all elements of the catalyst surface in the same way. For a large rate constant, poisoning occurs at pellet exterior as soon as the poison reaches the surface. So we saw the different sides to the restoration process. So how it get deposited, where it get deposited, if it's the surface or the exterior and the interior. This is how it is affected. Now moving on to the last factor, that is additional factors influencing the decay. All the other factors that contributes, that are minor factors, and we have clubbed them together, and here we will see them. Numerous other factors may influence the observed change in the activity of catalyst. These include pore mouth blocking by deposit solid, equilibrium, or reversible poisoning where some activity always remains, and the action of regeneration. Most important of all, the observed deactivation may result from a number of processes at work simultaneously. Although the possible influence of all these factors should be examined in the real case, in this introductory treatment, we will concentrate on the first two factors, the decay reaction and pore diffusion. There are enough lessons here to illustrate how to approach the more complete problem. Now, the rate and performance equation. So, the activity of a catalyst pellet at any time defined as A is equal to rate at which the pellet converts reactant A by the rate of reaction A with fresh pellet, that is minus R dash A by minus R dash A. And in terms of the fluid bathing, the pellet, the rate of reaction of A should be of the following form. Reaction rate is equal to F1 into F3 into F5. Here, F1 is mainstream temperature, F3 mainstream concentration, and F5 present activity of the catalyst pellet. Similarly, the rate at which the catalyst pellet deactivates may be written as deactivation rate, which is equal to F2 into F4 into F6, which is mainstream temperature, mainstream concentration, present state of the catalyst bed. Now, in terms of nth order kinetics, Arrhenius temperature dependency, and isothermal conditions, the equation 2 becomes for the main reaction, and minus R dash A equal to K dash multiplied by CNA dot A, and this is the reaction which justifies it. And for the deactivation, which in general is dependent on the concentration of gas phase species, equation 3 becomes the given equation, which is given below, minus dA by dt is equal to Kd into Cmi into Ad, and this justifies this process, where D is called the order of deactivation, M measures the concentration dependency, and Ad is the activation energy or temperature dependency of the deactivation. In certain reactions, such as isomerization and cracking, deactivation may be caused both by reactant and product. Since Ca plus C remains constant for a specific feed, this type of deactivation reduces to the simple to treat independent deactivation. Although the above nth order expression are quite simple, they are, in general, enough to embrace many of the decay equations used today. The rate equation from experiment. Here we are going to show the experimental rate equation. The experimental devices for studying deactivating catalysts fall into two classes: those which use a batch of solids and those which use a through flow of solids. Now, batch solid devices can only be used when deactivation is slow enough. When deactivation is very rapid, then a flow solid system must be used. Batch solid, determining the rate for independent deactivation. Here, it is illustrated how to interpret experiments from the various batch solids reactors and how to manipulate the basic performance equations for these reactors by testing the fit for the simplest of equations forms for independent deactivation. Here are the two equations given, 6a and 6b, which is minus r dash a is equal to k dash ca with f equal to 0 and minus dA by dt equal to kd into it. This represents the first order reaction and the first order deactivation, which in addition is concentration independent. As we can see, there is no concentration in that equation 6b. So that's how concentration independent. Now, batch solids and batch flare. We have the equation ln of Ca divided by Ca infinity is equal to ln Wk dash divided by Vkd minus kdt. A plot as shown provides a test for this rate form. So as we can see that the curve is a straight line which we have plotted in ln of Ca by Ca infinity versus t, and the slope of this line is minus kd. Now moving on, batch solids, mixed constant, flow of fluids. The equation here is ln CaO by Ca minus 1 is equal to ln k dash tau dash minus kdt. This expression shows how the reactant concentration at the outlet rises with time, while the plot provides the test of this kinetic equation. Here we plotted the curve between ln of CaO by Ca minus 1 and t. Again, the curve is a straight line with a slope that is equal to minus kd, and we have the y-intercept is equal to ln of k dash t dash, as we can compare the above this equation with y is equal to mx plus c. As we compare, we get the slope and intercept as shown in the graph, equation 26. Moving on, batch solids batch solids mix changing flow of fluid to keep C fixed. Here concentration is fixed. To keep C a constant, the flow rate must be slowly changed with time. In fact, it must be lowered because the catalyst is deactivating. So this equation is given to justify this. Figure below shows how to test for the kinetic expression by this procedure, which is on the next page actually. Here we again draw the curve. Now this curve is between ln of tau dash and t by using this reaction. We compared it with y is equal to mx plus c and we get this curve. On y-axis we have ln of tau dash, on x-axis we have t, and the curve again is a straight line with y-intercept as ln of co minus ca by k dash ca and the slope equal to k. Now as we move farther on the y-axis, there is a decrease in flow rate. So this was all about this presentation on the topic of mechanism of deactivating catalysts. Here we study how the catalyst deactivates, how it affects the reaction, and what are the factors that affects the decay, and how to reactivate or regenerate the catalyst. Thank you very much. This was the presentation. Thank you.